Okay, well, let's get started. I know many of you have many exams these 2 weeks, so everyone is a bit tired, right? A bit stressed out. But we have to go on, even though this is not included in our midterm exam, it will be included in the final exam, right? So, but we will try, not to go too fast or too intensive in the lectures, yeah, so that everyone, can not be too stressed out, yeah. Yes.
Slightly unrelated question. I'm just curious, because we recently got our assignment, programming assignment 1 marks back, but we didn't get it with any feedback. I'm just curious if either for this, maybe not for this assignment, I don't know how soon it can be, but for the future programming assignments.
I saw the question on Piazza. I have not talked to the TA yet. I was hoping for them to respond. If they have not responded, I'm going to follow up with them to see whether they can give you some comments. Yes. Yeah.
So should we wait for approval from the teaching team that whether we can do it on March 7th?
I have looked at the people who want to sign up on Thursday. Everyone is okay, so I allowed that. If you sign up already, you will be taking it on Wednesday. Yeah. Okay, so we'll start talking about unsupervised learning in these 2 weeks. Okay, and basically now you have a set of data that has no labels, right? So it's the scripted D, just a bunch of X values. Yeah, and well, let's say Xi is D-dimensional data. Yeah, the thing to know here is that there are no labels. Yeah. Okay, so what can we learn from this? Now, if we think about supervised learning in terms of the analogy that we have at the beginning, which is a baby learning what a tree is. Yeah, then you have the mother, a guardian, telling the baby this is a tree, that's a tree. Those are examples that we have. Those are label examples, right? They are labeled as trees, or this is a cat, that's a cat, and that's a dog. Yeah. Here we don't have those labels anymore, and yet we still want the machine to learn something. Yeah. So in other words, you just give a baby a bunch of items. Maybe this object is somewhat green looking and kind of grow from the ground. Yeah, it kind of stays on the ground. And then over there, there's this furry thing that can run around. Yeah, and you want the baby to learn their different things. Okay, there's no label, so the machine would not know what they are called. But learning categorization of different objects is almost as good as giving them a label, right? Because the label doesn't really mean a lot. You think about it. Whether you call it a tree, or cat, or dog, these are just English words, right? You can think about another language. You have another set of labels, but they mean the same thing. Yeah? So categorization itself is the main thing, right? And that's what we want the machine to do without a supervisor. So you can think about this. It could be a more challenging problem than supervised learning, right? And that's true. Yes?
So the labels were the whys in the past 2 weeks?
Yes, yeah, that's right. So one example of this kind of D would be, well, it's just a set of documents, yeah, and you don't know what they are about. The machine doesn't know anyways. And the Xi, one Xi could be the set of features could be the histogram of the length of the words in a document. Yeah, so that's a histogram of a word length. In document I. Yeah, everyone knows what histogram means, right? Just counting how many of the words have this length. Yeah, that's the histogram. And so you get a vector of different lengths, of word lengths. And you can imagine having this information, well, just by human beings, we can know, well, if I know the histogram, I might know maybe one document is fiction, another one may be a news story, another one might be a scientific document. Yeah, the idea is that, well, maybe for scientific documents, the writers tend to use longer words, more complex words. Yeah, whereas for fiction, maybe shorter words. Yeah, for example. Okay, they'll give you some information. Yeah, that's just one example. What can we do with this? Yeah, so you can do clustering. You can try to categorize these documents or categorize your data points, in whatever they are in general, into different groups. That's what we call clustering. And in the example of document would be, I can tell whether this document is fiction or news or scientific writing and whatnot. Another thing you can do is density estimation. Density here means probability density. What is the probability of seeing, say, that kind of word length, that kind of histogram of the word length? And what can density estimation help you? Why do you want to know the density of these features, these X vectors? Well, one example is currently I'm working on a research project with tellers where they want to use machine learning techniques to identify traffic types. When the network traffic comes into their network, they want to know. Nowadays, they're all encrypted. You cannot see inside the packets. But you do want to use the statistics of those packets, those flows, to know what they are. Maybe they are Netflix or they are emails or not. Okay, and one important application of that is, well, maybe it's attacker's traffic. It's not something that you see normally. Okay, but then in order to identify attacker traffic, this kind of abnormal traffic, you want to know what does your normal traffic look like. Okay, and you have a variety of traffic coming into the network, right? So what do you mean by normal? Okay, so density estimation would be one way to find out what is considered as normal. You have density, right? A shape, certain shape. More likely that it's here, less likely to be there. So if you see some traffic that's way out there on the tail side of your density, then you know, okay, that traffic you want to pay a bit more attention to it because it looks unusual. Yeah, makes sense, right? So density estimation. Yeah, nevertheless, you want to preserve the privacy of your customers, but at the same time, you still want to protect your network if it's an attacker. Yeah. Yes.
I guess just sort of brings a question. What type of tasks are usually better for, let's say, unsupervised learning than supervised learning? Because it seems like the way
you don't have a choice. It really depends on what kind of data you have, right? If you have data that has no label, then you do unsupervised learning. Yeah. Because having some label is always better than having nothing, right? Having a supervisor to help always better, yeah. Oh, assuming the supervisor is correct. Yeah, that's right. Yeah, especially density estimation. Good for identifying outliers. Yeah. And another thing is feature processing that you can do. Just look at the feature, you can process them. We touched upon this a little bit, right? The PCA, the principal component analysis, that you can rotate the features, you can transform the features into something that's a bit more recognizable. Yeah. So that you can do as well without the labels, right? Without the labels, you can do that. And including also, one example is dimension reduction. Yeah. Make your complex data a bit simple to look at. So, but we're not going to be able to cover this part in our course. So we just focus on clustering and density estimation. Okay. So let's go to clustering. So the idea is that you're given these data points, n data points. You want to separate them into different groups. You want to do that because in the later, during the testing phase, you get a new data point. You want to know which group this data point belongs to. Yeah? Okay. So you partition your training data D into, let's say, K disjoint clusters, or just groups if you want, right? But cluster is the kind of the more scientific name commonly we use. So K would be, of course, much less than the number of data points you have in general, right? If it's close to the number of points, then the grouping is not that meaningful. And such that the elements in each group, you want them to be similar to each other. And that's why you group them together, right? So they have to be close to each other in some sense. so such that the element in each cluster are close to each other. Yeah, then you group them. So how do we describe this mathematically? Well, if we describe the closeness, we define the closeness as Euclidean distance between the vectors. Yeah, then we can write that. That's one way to do it. So mathematically, let's say, given the data set D, we want to output the groups, the group membership, right? So the clusters. We denote them by S1, S2, to Sk. We want to have K groups. Each group, of course, is a subset of this D, right? It has to be partitioned. So that means no overlapping, and then the union of these groups have to form the original data set, right? So therefore, we need such that the intersection between any two groups or two clusters is the empty set, right? This is for all ij. And then the union, I from 1 to k, has to go give you back the original data set. Right? That's what we mean by partition. Right? Not only we want to have the clusters, just basically the groups of points. In order to represent the clusters, instead of just call them 1, 2 to k, we use what's called cluster center as a kind of a label for the cluster. Okay? So we also want to have a second thing called cluster centers. I'm going to use American spelling here. Just follow the textbook because I don't know which one I use ER, which one I use RE otherwise. So I'll just stick to ER for all of them. So mu I. Each one of them, of course, is it is in d-dimensional space. Yeah, the d-dimensional space of your data points. Okay, so these are the so-called cluster centers. Yeah. Eventually, we'll get there. Yeah, turns out to be the mean. Okay, but for now, let's say each cluster has a cluster center. Okay, and we want to find the optimal clusters and the cluster centers. So a quick example for the case of two-dimensional space. Yeah, so you have x, x1, x2, like that, and you have some, points like this. I don't know. Let's say here. Like that, maybe. Yeah, these are your data points. And let's say you want to cluster them into two clusters. Yeah? What would that look like? Again, because our human brain is very well trained for pattern recognition. You look at this, you say, well, I have to make two clusters. Looks reasonable that one here, one there, right? It's pretty easy for our brain to solve this problem, at least in this lower dimension space where our brain is more used to. Yeah, higher dimensional space, our brain does not work at all. Right? We are not trained in more than 3 dimensions usually. So let's say this one is a cluster, and then we have another cluster here, S2, right? So that's the kind of problem we're going to solve. And then there's going to be cluster center. Let's say it's right here. Yeah, let's call this mu1, and maybe this one is mu2 over there. Yeah. Notice that the cluster centers, they don't have to be one of those data points, right? Yeah, they're just a representation of the cluster, but it is in the same space. Yeah, it's in the same d-dimensional space. Okay. So now, well, we can do this by our brain, but then how do you teach a machine to do this? To teach a machine to do this, you say, well, I have to define what we mean by a good cluster, a clustering scheme. Right? What is good clustering scheme? That means you have to have some kind of a measurement for goodness, or let's say the measurement for error, as we have done before for the supervised learning. Yeah, the E-in, the in-sample error. Okay, so let's define that. So we define the error measure. For now, let's say let's say EJ is the error for that cluster. What do you think? Very often we use this clustering so that we can group them, and then we say that the mu1 will be a representation of all of the sample points inside S1. Mu2 will be a good representation of all sample points in S2, right? Yeah? That's a major reason that we want to cluster, so that we can group them into two groups, and then one group, they are similar, they are all very similar to mu1, and then the other group is very similar to mu2. With that in mind, what would be a good error measure? Yeah. This is one good way to think about it. You want them to be far apart, okay? Yeah. But that may not be the best idea, because in that case, the two mu's will be right all the way spread out on the two sides, right? They may not be the best representation of your original data. Okay? So what is another way to measure the goodness of the representation? Yeah? Variance within the cluster, yeah. Yeah. So how far away are the data points from the cluster center? Yeah? The sum distance of the data points within the cluster to the data center. To the, not distance, the cluster center. Yeah? Okay? So we define that as this one. Among all of the points xm that's in the cluster Sj, yeah, what is their distance to the cluster center J? And yeah? Square distance. Okay? That seems to be a reasonable measurement of error, right? Yeah? You want the distance to be small, then this mu will be a good representation. Okay? So, and we also call this the approximation error, in the sense that the mu j will be considered as an approximation for all of the data points inside the cluster. Right? For the cluster Sj. Okay. So then, of course, now we can define for all of the clusters, we sum up all EJs. That would be our E in, right? Our in-sample error. But notice that this is a in-sample. What kind of parameters do we have? Well, our choices would be these two things, right? The clusters that we define, and then the cluster centers. Yeah, those are the parameters for our learning. So this E in will be a function of S1 all the way to Sk, and then the mu1 to mu k. Yeah? And we simply defined it as the summation of j 1 to k ej. Yeah? The sum of all of the errors within each cluster. Perfect sense? Makes perfect sense, right? It's quite straightforward. Yeah? So the sum approximation error of the cluster centers. Okay? Yeah?
So, which one is the approximation error again? Is it EJ or
EJ for approximation error for cluster Sj. Yeah? But then you can, because of that, you can understand E in as the total approximation error for the entire data set.
Thank you.
Yeah? Okay? No worries. Yeah. So, in fact, this brings up a good point. So we have a different way to express this E in instead of summing over the clusters. You can also sum these errors over the sample points themselves. Okay? So what I want to say is that this is equal to another way to sum, n equal to 1 to n. If I want to sum over all sample points, what would that look like inside the sum? The distance of each sample point to its own cluster center, right? Whatever that cluster center may be, right? The distance of the sample point itself to its own center. But in general, we don't know at this point which center it belongs to, right? Let's just write it as a function of mu of xm like that, yeah? So here, where mu of xm will simply be defined as the center of the cluster that xm belongs to, right? Center of cluster, I do fancier than to which xn belongs. Yeah. Everyone agrees? Yeah. I can write this in terms of a per sample sum. Yeah. Instead of per cluster sum, it's the same thing. Yeah. So in different parts of our analysis, we're going to use either one of these representations of the in-sample error. So then our learning problem obviously would be just to minimize this E in, right? Find the optimal S and the mu's to minimize it. So I'll just write it down. Our learning problem is to minimize over all possible S1, Sk, and then the corresponding mu1, mu k, this E in, the in-sample error, S1 of just E. Yeah, that's what we want to do. And once you solve this problem, suppose you find the cluster centers and the clusters, then we can talk about what is testing, right? Testing and inference. We're going to talk about how to optimize this later, but suppose you can do it. Yeah. So inference, of course, when you are given a new data point, yeah, a new data point called x, let's say. Do I call it x? Yeah. What you want to do, we just want to know which group it belongs to now. Yeah. Once the training data set tells you how to group things in this D-dimensional space, you given the new one, you say, well, which group does it belong? That's the inference job. So to which cluster does it belong? Yeah? So that's the kind of question that we can solve by unsupervised learning. Yeah? So basically, you learn to group test data, yeah? Data that you have not seen. Now you know how to group them. So of course, clearly this application will be, say, classification. Yeah? When you don't have the labels, you still want to classify them into some categories anyways. Yeah? The classification of documents. I think there's an example in the book on coins and so on. Doesn't really matter. It's just the classification without labels. And then another application of this would be recommendation systems. If you know that a new user to Netflix, for example, yeah, you just observe the attributes of this user. Does it belong to this group or that group? Yeah, that group division will be separated in some way. Okay? And then you recommend movies based on which group this user belongs to. Yeah? Oh, I'm sorry about that. Part of my research is in wireless communication systems. So interference is a very important problem. So inference. Yeah. Thank you. So this, I hope you're convinced that clustering is an important learning problem to solve. But unfortunately, this problem is very hard. In fact, it's MP hard, okay, to find the optimal clustering. So I'll write it down. Is MP hard. Okay, so the only hope that we can find the efficient solution is through heuristics. So what would be a good heuristic to solve this problem? Basically, that's what we're asking. Okay, and the best known heuristic, also very effective, is the famous k-means algorithm that I think many of you have already heard of, yeah, at some point in time, k-means. K-means algorithm of clustering. And the original solution was proposed by Lloyd, so it's also called Lloyd's algorithm, 1956, yeah, a long time ago. And k-means clustering, it's a pretty straightforward algorithm, and it's in the 50s, right? Things are not very complex. And it is an alternating optimization approach. Remember, we have to optimize what? Two groups of things, right? We have to optimize S and mu's, yeah? So the idea is to alternatingly optimize them back and forth, back and forth, back and forth. You cannot just one-shot optimization because that would be very hard, yeah? The idea is to just optimize one, holding the other fixed, and then optimize the other one, holding the other one fixed, and keep rotating until it converges. Yep. So it is an alternating optimization approach. With two subproblems. So first one, is given S, we found mu. Yeah? Given the cluster membership, you already know that. You want to find the best cluster centers, again, to minimize the E in, right? That's always our goal. Yeah? Find, oh boy. Try to reset my pen. Find the centers mu1, UK, again to minimize E in. Yeah. Now, of course, as a reminder, E in is simply this guy, right? EJ, yeah, 1 to K. Okay. And immediately you see that, well, those, given the clusters already, those EJs are independent of each other, right? Those clusters, they don't have anything to do with each other, really, when you try to find the best center for each cluster. Yeah? So that's turns out to be an easy problem, right? EJ is simply, well, xn in Sj, I'm just rewriting what we have over there, minus mu j square. And this depends only on Sj, yeah? It does not depend on any other cluster. So therefore, we can simply find the optimal mu j within each cluster, yeah? For each j, we just take the minimum, mu j, that's in d-dimensional space of that thing with the sum. Well, let me just write it. Probably didn't have to write so many times, but anyway, yeah, that's what we need to solve. In each cluster, we want to find the best cluster center to minimize the sum distance. Yeah. How do we solve it? And as already suggested, just the average of those data points. Okay, but that's so-called centroid of those data points, right? So in fact, looking at this minimization, it is, you're actually trying to find the centroid of Sj, yeah? And if you remember, I don't know, your high school stuff, and that's the centroid is simply the average of those points. But let's prove it, since we, have enough knowledge to know how to find this minimum already, right? It's a quadratic problem. So to find this minimum, we just take the gradient and set it to 0, right? Let's take the gradient, set it to 0 and see what happens. Gradient with respect to mu j, yeah? And then this sum. Oh, I'm writing this again? Okay, that's why. It's n minus Sj, like that, yeah? Equals 0, right? That's what we're trying to do. And gradient and the sum, we can swap the order, yeah? Both of them are linear, so I get the sum xn is in Sj, and then the gradient inside, yeah? The gradient of this square term, by now you should all be very comfortable with taking this simple gradient, right? Yeah? You might be expected to do it for the midterm exam, right? Not the difficult ones, but simple ones like this, you should be able to do yourself. This is a derivative of a square, so just 2 times, yeah? 2 times that, xn minus mu j, and then you take the derivative of inside, yeah? Chain rule of differentiation, there's a minus sign, that's all, right? There's minus 1, like that, has to be equal to 0, yeah? The 2 times minus 1 can be deleted because it's just 0, right? And then you have this sum of this difference has to be equal to 0. But what does this mean? So what does mu j equal? Mu j is a constant with respect to the xn's, right? So you can take the constant out, throw it to the right-hand side, right? But when you take out the constant, you have to watch out. There's a sum here over that many points. So the total number of points inside S multiply mu should be on the right-hand side, yeah? So when you divide it through, this you get 1 over the size of Sj, yeah? And then summing up all of these points, xn, right? Yeah. So indeed, this is the average of all of the data points, yeah? So we have to show that it is the average. And that one minimizes our E in, yeah, given the S in Sj. Yeah. So now we have solved the subproblem number 1. Given the cluster membership, what are the optimal centers? So let's solve the second one now. Let's look at the second one, subproblem 2. Given the centers, okay, we want to find the cluster memberships Sk. Again, always remember your goal, right? To minimize E in. Yeah. Now, what does this problem look like in this side of the problem? Let me go back to that picture that I drew. I'm going to make a copy of the picture, move it over here. Copy. Here, just like that. I'm going to erase this. Well, because at this point we don't know the cluster, right? Here, at this point, we just know the cluster centers. Great. Okay. So you still have this data set, of course. Your training data, you always have it. Training data, you always have them. And then you also have the 2 cluster centers. Now you say, okay, now I have to update the cluster membership. What would be the best cluster membership to minimize E in? Yeah, remember what E in is, right? The approximation error. Okay. So basically, you're saying, for this point, for example, do I want to group it in cluster 1, or do I want to group it in cluster 2? Yeah, and then you look at this data point and say, do I group it into cluster 1 or cluster 2? Which one is better? What do you think? How should we group? Yeah. So let me write it down first. I.e., again, given the data points, say xi, that's in your data set. And then we want to say which cluster it should belong. Yeah, so with which, let's say cluster should be associated. Bit clunky way to write this, but anyway. Yeah, we want to find the membership of that data point. That's the problem that we want to solve. Yeah. Okay. We already know the representations for those clusters, yeah, which are these cluster centers. We know their representatives or representations. Now you have to decide which point belong to what. So, yeah. Yeah, seems reasonable, right? You want to minimize the total distance. Then you just, whoever that's nearest to me, then I belong to that cluster center. Yeah? Just pick the nearest cluster center, and then you should be that one. That seems to be a good thing to do, but let's prove it. Prove that it is, in fact, the best thing to do. Yeah? So here we're going to write this E in using the form of summing up all of the data points. Like this. So remember, mu xn here is the data center that xn is associated with. Yeah? And that's the data center that we have to find, right? We have to find out what this mu should be, yeah, for any particular xn. But you notice that this sum can be, only one of them involves the xi that I'll be interested in, right? In particular, now we're looking at xi, yeah? So you notice this sum is sum of all n. Only one of these terms involves xi, yeah? Oops, no, that's it. This plus xi, the i's term here, mu xi. Yeah? All of the others are irrelevant, right? When we look at this particular data point, we ask which data center I should choose. When I minimize E in, only this one term matters, yeah, for that decision. Okay? Therefore, all that I need is to minimize this. Yeah? All that I need to do is to minimize this square term, which is simply the distance between xi and the data center that you pick, and the cluster center that you pick. I kept saying data center. Yeah? That's too much influenced by Google. Yeah. So this is the only term involving xi, among the sum of n terms. Only one has to do with that point, so just minimize that. Yeah. So mu xi is equal to the argmin among all of the possible cluster centers, which is mu1 to mu k. Yeah. Among all of them, you choose the one that minimizes the distance to xi. Yeah? And then by doing that for every single data point, then we can minimize E in. Yeah? So the idea is very simple. So i.e. xi should be assigned to the nearest cluster center. Yeah. So now we solve subproblem number 2, also very simple problem to solve. Yeah. So each step, the problem is extremely simple to solve. Yeah. And then we're just alternating, update one and then the other, and then keep going back and forth. Every time you do this, you get a new membership, right? Then you have a correspondingly, you have a new set of cluster centers. Yeah, with that new set of cluster centers, now you have another new set of memberships. You keep going, hope that it converges. Okay? So if we write this out in just a algorithm form, do I have space? Yeah, let's just write it here. K means algorithm. Hmm? Yeah, it's very difficult, turns out. For now, let's say that it's given to you. You know what K is. We're going to have a bit discussion at the end today, okay? So let's write down this formula first. First of all, I'm not going to write the input. That's given D and K. Yeah. Well, maybe I should write. Yeah? Maybe just say input D, scripted D and K. Yeah. And then you initialize. You just have to get the whole iteration started, right? Just initialize some cluster centers. That seems to be easier than initializing the membership. And usually we just initialize them at random, yeah? Very common thing to do is just pick some uniform points, pick K points uniformly in your space. And then you, using these cluster centers to construct the clusters. S1, S2, of course, SK, by solving subproblem 2, I guess, yeah? Yeah, basically just group the points by the nearest, with the nearest cluster center. And then second, and then now you can update the cluster centers based on this new membership that you have. By again solving subproblem 1, yeah, which is just the centroid problem. Just take the average of the members inside the cluster. Very simple. And then you repeat. Oops. Repeat. Come on. Steps 2 and 3. Until convergence. Okay. Idea is very simple. It was first proposed by Lloyd, but there's of course one quick big question. Whenever you see an algorithm that says until convergence, you have to ask, does it really converge? Yeah. What is the where does it converge to also? Yeah. No guarantee whatsoever for Lloyd's algorithm. Yeah. Yeah, does it always converge, basically? Fortunately, it does. It always converges. You can prove it. Yeah? So that's the note that we're going to discuss first. 1, convergence is guaranteed. This is because if you look at E in over the steps, every step you just update one part. Right? Either up the mu or up the S. You always optimize. You can solve this optimally. Very simple. Yeah. So every time you reduce this error measure, yeah, you make a smaller approximation error. So E in always reduces in every step. Okay. So it keeps going down. At the same time, E in is the distance, right? It's greater than 0. So it's low bounded by 0. Okay. You have a sequence that's always decreasing and it's low bounded. By the monotone convergence theorem, you always have convergence. The limit always exists. Okay? So that's the idea. It's well, more precisely, not always decreasing, but this is non-increasing. Because you always do a little bit better every time. In steps 2 and 3, yeah, and it is low bounded. Has anyone heard of this monotone convergence theorem? Yeah, kind of, maybe in some, I don't know. Huh? Yeah, some kind of calculus, I guess. Yeah. Yeah. If the opposite also works, right? If you always have a kind of increasing sequence and upper bounded, then it's also, it guarantees convergence. So, which is very nice. And the second thing is that it turns out that you can show this is locally optimal, but there's no guarantee for anywhere close to the true global optimal, okay? But once you get to convergence point, around the neighborhood of that point, it is the best point. That's what local optimal means, right? Around your neighborhood, you are the best. But then there's no guarantee that over the entire space, you are the best. Yeah, you're not the global optimal, okay? So that's that. Now, going back to your question about how to choose K. Here we assume that it's given to you ahead of time, yeah? Okay. So what do you think would be the best K to use when we have to run K means? Yeah?
Maybe I would start with for a large K,
Okay, and then what you hope to do? There's some kind of optimal K?
Because the reason is that sort of the larger the K is,
Mhm.
fitting for noise.
Looking for noise. Okay, could be.
So you want to
Could be.
decrease it until it's sort of increasing to
Okay.
a threshold.
Yeah. But yeah. So let's look at the E in that you have, right? Over K. So this is K. Okay? E in. What do you think this E in look like as you have more and more clusters? Keep going down. How big K can be? Number of data points you have, which is n, right? At n, what is E in? 0, right? Because every point is its own cluster and its own cluster center. Yeah? You always stop at 0 here for E in. There's no hope to find optimal K. Yeah? The optimal K is at n, which is meaningless. Yeah? You're not doing any grouping at all. Then you say, well, my hope is then, how about E out? Does E out go up like what we see before, right? In supervised learning, maybe E out go up. Are you sure? Think about it in doing testing. Yeah, it's actually the best thing, right? If you want to just minimize the distance, right? Okay? The more points, the better. Do you mean? So E out also goes down, unfortunately. It doesn't, go as fast as E in probably, yeah? It goes like that. This is also E out. Okay? So E out also decreasing. So therefore, that tells you that there's no optimal K that you can choose by just looking at E in and E out, just by looking at the distance. Okay? So you have to find something else to define your optimal K. Okay? For K means. Yeah? So something else, for example, it could be the cost of building a system with that many clusters. Yeah, maybe your cost is a increasing function of K. Okay, so on the one hand, E in goes up, but then your costs go up, and then the optimal is somewhere in the middle. So, but then K means cannot help you consider that. Yeah, that consideration for cost is outside of K mean. Yeah, K means. So K means will not tell you how to choose optimal K. That's something to keep in mind. Okay. Yeah, has to be something else. You have a question first? Yeah. Yeah, just this is no, it's just the distance, right? Remember, it's the distance to the nearest center. Yeah, the distance to the nearest center is my measurement of approximation error, right? The more points you have, the more likely you will find a closer distance, closer point to you. Yeah, you first. Yeah. Well, E out would also, let's just define it as the approximation error. Yeah, basically, I will have to pick the optimal cluster center. My distance to the cluster center would be my error.
So E out would basically be error of any new point.
Yeah, that's right. Yeah. I think you first. Yeah.
I guess, yeah, we randomly initialize the centers, right?
Yes. Yes. Yeah.
Is there like a different schemes to choose?
Very good point. Yeah, we don't have any good way to choose this initial point. One way is that in question algorithm studies, you try multiple times, different initialization, and pick the best one at the end. Yeah.
Does this assume that like the data points, like each cluster is somewhat spherical in shape?
No, we don't assume that at all. It kind of, because here we use the Euclidean distance. So kind of like we define a sphere for the distance. Yeah, but not exactly a sphere because these are discrete points, right?
I'm kind of guessing that if there's like a data point,
Mm-hmm.
right? That's not exactly like close to somewhere, but if it's like densely packed but in a long shape,
Yeah.
then I feel like its edges could kind of trail off into a different cluster when it's clearly, packed with another one.
Yeah, in fact, there is actually another thing that usually I also say. It's a so-called Voronoi cell. I urge you to search for this, Voronoi tessellation. That's what you get at the end of the k-means, okay? But this one I will make it maybe just optional, yeah.
So I guess, like the way it seems to me then is like we have to know ahead of time how many clusters we expect.
You have to find a way to decide that.
Like for example, if it's like the coin, for example, we know that there's only set denomination.
Yeah, exactly. Yeah.
So like, I guess that's.
Yeah, if you have to find this optimal k from something else, basically. Yeah. But that's not the problem of k-means. It's an input.